Okay, today's somewhat of an intense day. Lots of stuff we're going to cover. So really try to concentrate and stay with me. We're going to start by going over the homework. So the first, we've got this graph. The red graph is the output is area of a square, right? And the input was x is the side length of the square. So we're going to put, that's the red graph. And then what is our black graph? What is our black graph? You can hold on to your homework. You can look at it while we're talking about it. It's fine. The black graph. What is it made of? Is piecewise? It's piecewise made up of what kind of thing?
Constant rates of change.
Okay, constant rate. Specifically, what kind of constant rates of change?
Average.
Average rates of change, right? Since we talked about the last couple classes, we've got a piecewise function made up of average rates of change. And how's it doing it? Kind of mimicking the area function, that square area function. Pretty good, right? Very little daylight between our the actual function and the this average rate piecewise function. Okay, so and I asked you to find all these average rates. Really, I think you couldn't find the sixth one. I didn't give you enough room, right? So there's these first five we should have gotten.
If I put 0 for to make it 6, will it count? Because I can only find the first 5. So
yeah, just the first 5 is what we're going to look at. That's fine. So you should have gotten something around. So you could have either estimated y values of these points based on the graph, or you could use the function. The function is very simple. What's the function? F of x. What's our rule for this function if it gives us the area of a square whose side length is x? Yeah, did you know that's why they call raising to the power 2 square? Did you know that? That's why when you raise to the power 2, they call it a square, because it gives you the area of a square. Things they never told you, right? The things they never told you. So you could have gotten these exact y values, right? You could have gotten these exact y values, or you could have picked them off from the graph. In any case, here's the average rates that you should have gotten if you did it right. About, approximate. How did you do? So these are just approximates. Should be in the ballpark. If you're not in this ballpark, then you didn't calculate your average rates of change correctly. Don't start scrambling to redo computations now. This is not the right time to do that. Okay. Let's just do one together here. We'll just do one. We'll just do this one right here. So at point 4, it looks to me like about 1.5. So you got at about point 4. 0.15, but actually what is it in actuality? 0.16, right? It's x squared. And then at 0.6, let's just use the actual value. It's a lot easier. You know, we could pick that off. Oh, it looks like about 0.3, but what is it actually? 0.36, right? It's just the side length squared. The area is the side length squared. So your average rate of change for this particular interval is the change in y over the change in area over the change in. Should really be putting zeros in front of these. Okay, and so you get 0.2 over 0.2, 1. What is it? It's it's the relative size, so it's constant rate of change. So it's the relative size of the change in area to our change in side length. If for this particular side length increase from 0.4 to 0.6, when we increase by 0.2 for that particular, our area goes up 0.2 also. So that's a 1-to-1. That's a relative size of 1. Not exclamation point. That's my cursor. Okay, so just without erasing, and don't erase and right. Can you see how you were in error in your average rates if you didn't do them correctly? Hopefully most of you did them correctly. So these are average. Any questions about calculating the average rates for these? So yeah, so it's delta y over delta x because it's a constant rate of change, or the relative size of the change in y to the change in x. And what happens to the relative size of the change in y to the change in x with each new interval? So here we get the same change in x every time. What is the new change in y relative to the change in x each time compared to the last one? Yeah, so what's happening to these changes in y? They're increasing, right? They're increasing, so therefore the relative size of changes in y is increasing, 0.5, 1.0, 1.5, 1.75. Any questions on calculating average rates of change? Which are just, what are average rates of change? Kevin?
I don't have a question on calculating it. I just have a question on what you just said right now. You're saying like, as the x increases, then the y is increasing proportionally. So does that just correspond to the graph just increasing in general?
No, y isn't. All I'm saying is I'm just comparing changes in y here. What's happening to the changes in y for an equal change in x? What is it doing? Increasing. And so that's what we see in the numbers.
Yeah.
Because our numbers is reflecting the size of the change in y relative to the size of the change in x. So that's reflecting that increase. Okay? Other questions? So again, what is an average rate of change? No, that's how you calculate it. What is it? Marianne, want to try? Okay, has to do with that, but we skipped over the most important thing. Don't read, Shannon. Do you remember? What is it, Shannon?
That like it takes to
Yeah.
do the same thing, like the same. I don't know.
Yeah, no, you got it. So first of all, it's the constant rate of change. It's a constant rate. So we just got to be able to put words to it. The constant rate of change. That does what? Somebody take over.
Yields the same change in y for a given value of change in x.
That's right. So it will give us the same change in y as the actual function for a given change in x. Okay, so it's the constant rate that gives us the same change in y for some specified change in x. Okay, and we're seeing this great value in average rate of change. What's this great? By finding these average rates of change and piecing them together, we see this great value in average rate of change. What's this value that we have to it? What does it do for us?
It helps us calculate the rate of change for the whole function.
Okay, so it's giving us a kind of a rate of change profile. But what about these pieces that are shown by average rates compared to the original graph?
We give like a step function, kind of.
Okay, yeah, that's true. But so what I was getting at is the value is that we're creating a nice pretend accumulation function, right? We get a nice pretend accumulation function, and everything you were saying is true too. Okay, any questions before? Now we want to generalize it. Okay, now we want to generalize this, and so we'll just take these away. So, okay, and so we're going to pick this interval right here, say from here to here, and we've got some current value of x. Okay, so we're at this is our current value of x in this interval, And what do we want to do? We want to write a single line function that will generate the input. We said the input is current value of x. And in your homework, and you wanted the output to be the average rate, right? At that current value. Okay, so we'll call this R. We'll call this function R. So in very most general terms, what's the structure of R going to be? Just where is this going to come from that we're going to be able to set up this rule for R of x in the most very general terms? What do you think?
Is it still a square?
What's that?
Is the function still a square?
No. It can be any. It could be any function. This is any function f of x.
Could you use the left of x function that we previously used?
Okay, so we're going to use the left x function, but I'm stepping back from that. Just in general, when we set up this rule, what's it going to be in the most general sense? K delta x. What do you think? Agree with that? What is it finding? The output is finding average rate. This is K delta x average rate. So what do we need here in general?
Change in y or change in x?
He wants change in y over change in x. Is that what that is? That's what it is. So when we set up this rule, the general structure of it's going to be change in y over change in x. Okay, which change in y and which change in x? Well, for the average rate for our current interval, here's our current interval right from here to here. So James had an idea. How are we going to get, if we're doing change in y, how are we going to get the y values of these 2 points? So you said left of x. What does left of x get us? So if I said left of x, what would that be?
Beginning of the interval.
So something about this point? What about this point is left of x?
So A of left of x maybe?
Okay, you got it. You're just getting ahead of me. What about that point is left of x? The x value, right? If you put the current value of x in, it's left of x spits out the left side, right? And so what's the y value of that point? Yeah.
Is it the A of left of x?
Right, so we're calling it f, so this function's f.
So
The function is f.
So F of left of x?
F of left of x, right? So left of x gives us the x value at the left side. If we plug it into the function, it'll give us the y value at this point, right? Okay, and so what about this point? What are its x and y coordinates?
It would be left of x plus the interval.
Okay, and so we want to just use left. We just keep using left. So how can we use left x to do it? What do you want to do, Ryan?
Well, I think you said it right. I was saying what he said it better. Is the left of x plus the delta x?
Yeah, what you said was right. We just need the mathematical, right? We need the actual value. Yeah, so isn't the x coordinate of that point left of x plus delta x? And so what's the y coordinate?
Basically,
F, yeah, exactly. F of that. Exactly. Right. So now, set up the rule. Set up the rule. You can set up the rule. What's the general structure of the rule to get our average rate of change? Delta y over delta x. So you need a lot of room for your numerator. Anyone, somebody new? Think you got the, Caitlin, question, sure.
What is the y coordinate for the second set of coordinates you did?
Over here, this point here?
Yeah.
How do you get the y coordinate if you have an input and you have your function? It's the y coordinate. Yeah, so that's what the function does. It gives you output for a given input. And output is on the y, right? So you put in your x value into the function and it spits out the y value. So that represents f of, say, a is the output or the y coordinate when the input is a. Does that answer your question? So what's the input here? What is the x value right here?
What is the x value?
Yeah. Based on the current value of x, what x value do we have right there?
Left x plus change in it?
Yeah, left x plus change in x. So how are you going to get the y value of that point then on the function f?
I think, wouldn't it be left x plus change in x of f of x out of left x plus change in x?
F of your input, right? F of that. That's what we said. F of that thing. All right, so somebody new. Alexander, did you get it? Tell me.
F left of x plus delta x minus f left of x over left of x plus delta x minus left of x.
So this is what f left of x plus delta x minus
F left of x.
f left of x. Okay.
Then over left of x plus delta x
Okay.
minus left of x.
Yeah, and what's that? So what does the denominator represent?
The delta x.
Yeah, it's just that's what we have. We have delta x. I really wanted to make that look good, but it didn't work out. Okay. Does it make sense? So this is our, what? The input is any current value of x, and the output is the average rate in the current interval, because it's calculating delta y over delta x for the current interval. Yeah?
Do your delta x's always have to be the same? Like your intervals always
It sure helps. It makes everything, yeah, so it wouldn't have to be, but then all the mathematics would be very difficult. Yeah, but so by keeping it the same, then we get just one formula for all of them, right? Yeah, if you change it, then this rate function is very difficult to write. You have to do more than one line to do it. Yeah, so we do that by convenience. And it's the independent variable, so we're in control of it. We're in control of it, so we just say we're going to make our delta x all the same. Okay, so we've got our rate function. Was anyone able to come up with this on your own last night? Doing homework.
I
Pretty close?
pretty close, but
Good.
I was using the A of x.
Oh, that's fine. So that's what you used A's here?
It didn't come out in the graph.
Oh, so the graph calculator didn't work. But
Yeah,
Yeah.
I did A of x plus the 0.2, the delta x, minus A of x over the 0.2 delta.
if it's going to give average rates, it's got to be left x, right? If it's going to give us our average rates, then you're not going to put x in there. You got to put left of x and
Well,
left.
I think I had assumed since A of x had left of x in it, and it was already referencing that x, that I was using that. So I took an A of x, since it referenced the left, and added the delta x to it.
I'm not sure how a of x is the area function. It doesn't reference the left. It's giving it the area at any value, right? The area function gives you the area.
I understand this.
Yeah, sure, I know.
I was trying to figure out last night. I had assumed since the A of x had left of x in it, that I could use that.
That's what I don't understand. We have to talk about that later. A of x is just giving you the area for any side length, so it doesn't have anything to do with left of x. The area.
I think I went back to the other one where it was the rate. I'll show you.
Yeah. You're talking about the accumulation function?
I think
This
so.
big
I was trying
one?
to go from this. I was trying to go from that and then call it. I understand this though.
Yeah.
That's what
Christian,
I did. I just didn't do that.
Christian, did you have a comment?
I was gonna say I was starting to get there, but like I said, like I didn't think of using A of x. I thought it was just saying only in terms of left x use it. So I ended up at left of x, but then I just tried to get. I mean I just came this close.
Okay, good.
I'm glad I came to class.
All right. Okay, so this is our average rate of change function. This is our average rate of change function for a fixed delta x. Output's the average rate of change. Okay, so let's go to graphing calculator and see how it works. Okay, so what is f? F, a rate function or accumulation function? I'm calling f x squared. A rate function or accumulation function? Okay? How is it thought of as an accumulation function? Gives the accumulation of area. What accumulation of area? Of a square. Yeah, so if as the side length grows from what to what? So if f of x would be the accumulation as the area squared grew from what side length to what side length? Anybody? What's that?
I don't know.
Oh, I thought you said it. 0 to x. So as the side length increases from 0 to x, f of x will give us how much the area accumulated over that increase in x, right? What is r? So that's what we just came up with, right? What is r? R gives what? The average rate of change. Yep. It gives the average rate of change of area for the current value of x, right? The current interval. So the current value of x will end up in an interval. If we plug that x into this average rate function, it'll give us the average rate of change in that current interval. Okay, so let's graph it. So here I have, what am I going to see when I turn this on? She says a step function. What do you think? Agree with that? You going to see a step function or a piecewise function or a curve, or talk to the person next to you. I'm going to turn on this rate function that we just built with delta x of 1. What are you going to see? Okay. What are you going to see? Peter, what do you think? He wants a step function. Molly, what do you think?
A straight line represents average rate.
Straight line.
Wait.
Straight line on the rate graph.
Sorry.
That's okay. So not a step function.
Well, it's just one value. Sorry. One step.
But it's a function. We're going to put in all these different values of x for different side lengths. And for each one, we're going to get the value of the average rate of change in the current interval.
Oh, then yeah. So.
Using a step function. Ross? They're all staying step function. Nothing. Actually, so I got the steps at 1, right? So what do we have the steps at? 0.2, right? Point 2, something like that. There we go, 0.2. So this is, for the one that we drew, this is the step function. Or something close. Okay? So, what happens when we change? What is A again? What is the value of A now? What's the value of A represent? Okay. What's that?
Starting side length.
Okay, starting value of x, which in this case would be starting side length, right? So is starting is the value of x from where we start accumulating, in this case side length. So what will changing the value of A do to this step graph? What will the effect be? Oh.
Won't it just make it go farther back and farther forward?
Okay, so it's gonna move this value of A is just gonna move this step graph left or right. What do you think? Agree with that? People are nodding. What's that? What's that?
You have to remove the lines that you already have, so you can add more.
So what I heard you say is the whole graph will just shift left to right. Now you're saying something different.
Like let's say if you had A at negative 0.2,
Okay.
you would have another step function for that interval because you're adding more.
Okay.
Instead of if you had it at like 0.4, you're going to lose that first line that you had.
Oh, I see. So now what you're saying is it's just where it's going to start. So if I started it here, I won't see any of that. I'll see everything to the right, but it'll stay the same.
I think.
Okay. Yeah. Any other suggestions? Let's actually. So how about let's do it on. Let's change A by looking at the actual average rate graph. Can we write? Let's see if we can, and then we'll go back to the step graph. So can we write a y value that will give us that piecewise average rate graph? Can we do that?
You mean the L of X from
Yeah. Yeah. Can we write that L of X that piecewise average rate function? Could we write one line to write that? So what do we want? Now the current value of X will output what value of Y on the constant rate. Could we do it? So what's the general form of that going to be? What will our general form of that be? What kind of graph is it? Okay, and each piece is what? Each piece is accumulation. That's right. But in general, each piece is a line, right? And we're going to connect a bunch of lines together. What do we have to graph a line?
Oh,
Control Shift A. Okay, but can we do it in? So that would be doing it as a bunch of different, right? But can we do it in one line? Can we do it in one line instead of a bunch of different pieces? So what was the form of our linear function? What form do we use? Remember? Everything we got to remember everything we've done, right? So it's not isolated topics, right? Everything builds together.
It's like point slope.
Point slope form, m times x minus a plus b. So now we're in a particular interval. In a particular interval, we just got to identify all those things, and then we'll get the function. So what is m in the particular interval that we have? Yeah, r of x. Right, that's our average rate that we've already done. R of x. Okay? We know x is just all x values. What is a?
Well, whatever A is.
So a is a point that we know, right? So we're in a current interval, and what's the starting point of the interval? We're going to use that starting point of the interval. What's the x value of that starting point? Left x. And then, what's the y value of the starting point? F of left x. So this now, in one line, should graph us this whole thing. Let's see, what's our value of... Where's my slider? Is it not just hidden here? There it is. So I got delta x at 1. That's good. Okay. So here we go. Zoom out. Did we get it? So now, changing the value of a. What will changing the value of a do to this our average rate piecewise linear function? Changing the value of a. I'm going to slide a. And what's going to happen? Let me ask you this. So will changing the value of a make this thing kind of detach from the graph and move away from the graph? Now, what will it do? Yeah, Ross or Aaron.
On it starting to get kind of closer to the other guy. Starts to I won't say it starts looking more lacking because of the great smaller segment.
So I think you got the wrong quantity. We're changing the wrong quantity. What quantity are you thinking about changing? Delta x. You're thinking about changing delta x. So that's what you said is correct, but for delta x, not a. So let's just do it. If we change a, watch what happens. What's going on here?
Can you turn off the red one?
Sure. Well, yeah. Or I'll make it. How about if I make it gray? There we go.
So all it's saying is moving it.
Why is it moving it, and how is it moving it?
Shifting it on the line.
Zoe, did you come with something?
I think I understand that, as A is changing where our left x is changing, so it's moving throughout the interval, because we're changing.
Yeah, we're just changing where we start from. If we have the same delta x, it's just going to move all it's going to do is move the endpoints of the intervals, right? All it's going to do is move the endpoints of the intervals. But the resulting graph will still keep trying to mimic our original function. So what will we see when I change a on that step graph? That's the graph of these constant rates. It's just going to kind of keep the same form, but just move different. All we're doing is starting somewhere different. So now our x intervals are in different places. That doesn't change what the rates are. I mean, it does, but the overall kind of profile of the rate, it doesn't change the overall profile of the rate. It just changes where the endpoints of the intervals are. Yeah.
So if we started with an A, and then we added A to it, would that be like the right step? Like, are we moving it like from left to mid to right, and then back?
No, we're actually moving the intervals. So we're actually shifting the whole intervals. We're not. It's not a matter of changing left or right or mid. It's just moving the intervals. It's just moving the intervals along the axis by changing a. Okay, so now Aaron wanted to. Is there a question? Aaron wanted to make delta x small. What's that going to do? So let's see. We can show both of these on the same graph. Okay, so here's our.
It'll start to mimic that gray line a little bit.
What's that?
I think it'll start to make that. It'll start to mimic that gray line a little more because you're shrinking your intervals.
If you shrink your intervals, then these average rates will do a better job pretending to be the real function, right? So then what will the step function do as I do that?
It's
Also shifting to small.
You're going to get smaller steps and more of them. And so here's the key. When delta x is very small, and now I change a, what is the effect of changing a when delta x is very small?
same thing.
So here delta x is, can I make it even smaller? No, it's too small. There we go. Let's do it in black so it shows up. I'm going to change a now when delta x is small. What effect does it have on the rate? Where you start accumulating from doesn't change the rate at a particular value. You see? If delta x is small enough. If delta x is small enough, where you start accumulating from doesn't affect. And what does left x when delta x becomes very, very small? It's like we get more and more and more and more and more and more left x's, right? So essentially, this becomes, when delta x gets small, what can we change left x to? No, left x. So delta x is like dx, that's right, but what about left x? Just x. It's kind of like, as it gets very, very small, then all these left x's are just like all the x's, right? They're just like all all x's. And so for delta x very small, we get this. Okay, so this was what? Approximating rate. Let delta x get very small. Delta x is very small, then what is this? What is that giving us? The rate. Yeah, the rate. So it's like exact rate. So what's that? Right. It's like an exact version of what we call Rx. So we call Rx. It's like because the average rate of change for the current interval, which was doing a really good job of matching the rate of change of the original function. So if we let delta x get very, very small, it's kind of like we've got an actual rate function, So if I pick, let's see. So we need to kind of bring this all together, we need kind of one more idea. So our reverse journey was a lot shorter, right? See, our whole forward journey was what? Exact rate to exact accumulation. It took us a month and a half. But we had a lot of tools that we built along the way. So now our reverse journey was from exact accumulation to exact rate. Well, we've practically got it with this expression right here for delta x very small. This is virtually our exact rate function. Okay, so one more tool that we need. Okay, is the idea of limit. So some of you were worried when you talked to your friends in other calculus courses because they started with limits. And we didn't, but actually we've been talking about limit a lot of the course. We've been talking about limit, we just never called it that. Okay, so now we're going to kind of formalize this mathematically. And so what's the idea here? So one idea of limit is this whole time we've been talking about delta x getting very, very small. So that's like a limit of 0. It's getting very, very small. The limiting value is 0. But another way to think of limit is like a never-ending sequence. So where is the girl taking, where is she actually, the girl taking the picture? Where would she be actually standing?
There.
Where?
Behind the camera.
Behind the camera. So relative to this image, where would she actually be? What's that? Standing behind the board? In front of the board. Left side or right side? She's in the left side in front, right? Facing the screen. She'd be like over here. Okay? And so this is the idea of a never-ending sequence. If you had enough light and there was and the mirrors were perfectly, so you can see they're not perfectly, as you go far enough back, you see a curve. That means we don't have actual perfectly parallel and perpendicular mirrors. But it would go on forever if they were, right? With perfect light and perfect right angles of the mirrors, it would be a never-ending sequence. Okay, so limits are, the idea is two representations of the same number. So you agree or disagree with this? If the symbols A and B represent different real numbers, then it's always possible to find a number between them, like the average. Agree or disagree? Agree, right? So this is what the real numbers are called dense. They're called dense. You pick any two real numbers that are different, you can find one in between, and you can do that infinitely. What about this? If they each represent a real number and it's impossible to find a number between them, then they're the same number. Would you agree with that? Are you sure? If you can't find a number between them, they've got to be the same number.
Why is it impossible to find? Is it impossible to find just because they're gigantically long and we don't have the processing ability, or is it because they're the same number?
I'm not following your question. So they each represent a real number, and this is a fact. You've got two numbers. It's It is impossible to find a number between them. It is impossible. That's fact. That's given. Conclusion: are they the same number or not? Same number. Got to be the same number. Okay, but you're not gonna. In a second, you're not gonna believe that. All right. So what about 0.9999999? Represents a number, right? The 9s go on forever. The 9s go on forever. Okay. So can you find a real number between 0.999, the 9s go on forever, and the number 1? Can you find a number between them?
Yes.
Tell me the number.
I don't know the numbers that you just said we could.
What do you mean? I
You
didn't-
were like, you're not gonna believe it in the next one.
Oh. No, can you find a number between?
We can represent it, we can't find it.
No, you can't.
Chloe, why not?
Because it's like 999 goes on forever and ever, since we use a base 10 system, there's no additional number that goes between infinite 9s and 1.
Yeah, so if you pick a number less than 1, this would always be greater than it, right? If you pick any number less than number 1, would this always be greater than it? Because you could take enough 9s, you get it to be greater. So what's the conclusion about these two numbers, 0.9999 forever and 1? They're the same. It's the same number. Do you believe it, Marco? You can't believe it?
Well, that's kind of what you were saying, so
Well,
it divides.
Yeah, it's one of the different types of infinite numbers. You can't divide by infinite. You can represent it symbolically, but you can't divide it and show the actual number, because once you show that number, it's going to change. It's like trying to say what's the last digit of pi. As soon as you figure it out, there's going to be another digit.
Yeah, but like I know the last digit of that probably.
Okay, so this is a number. Just like pi is a number, okay? Just because we can never write all the digits, it still is a number. And so is this, 0.998, an infinite number of 9s. It's still a number. So the question is it the same number as 1? Oh, you're saying no, so you don't believe this. If you say no, then you don't believe that second statement. Because it's impossible to find a number between these two. And because it's impossible to find a number between these two, they are the same number. Okay? But what?
Okay, but how can that be? Like, let's say one family has 2 kids, and then the next family has 3 kids. You can't have 2 and like a half kids. Like, you either have 2 or 3, so
Okay.
if they're not the same number. Like, do you know how? Is it just because it goes on forever that really we can't differentiate between that and 1? There's nothing in between it.
There's nothing in between the two.
So
That's
why you're just saying it's the same.
what's that?
So that's why you're saying that it's the same.
Right, based on this premise here, that if there's nothing in between those two values, if you can't find a number in between them, they have to be the same number. So that's the same thing here. There's no number you can find that's between this one and 1. The conclusion, therefore, based on this premise, the conclusion is that 1 equals, that they're equal. Yeah.
So kind of going back to the graph and everything, this is kind of applying to the graph where if we're getting really, really close to it, and we're going to have like numbers where they're going to be so close you can't actually figure out what the gap is, we're going to have to say they're going to be the real number or the rate that
Yeah, it's this whole idea of letting delta x get very small. But we're now kind of just exploring the general idea behind that, which is limit.
Does that mean like the reverse is true? Does that mean that like 1 over like an infinite number is going to be 0?
Well, this isn't an infinite number, right? This isn't. It just has an infinite number of decimal places. Okay, so it's not infinity. It just the places go on forever. So it's a little different. So you're talking about a number getting infinitely large. That's not what this does, right? This isn't getting infinitely large. It's just how many infinite number of digits. So it's a little different. Okay, so here's how we can express that. So it's really the sum of 9/10, 9/100, 9/1000, and then going on to 9 over 10 to some value, and then that, the number of zeros in our denominator then gets infinitely large. So this is our notation, the limit as n approaches infinity. So The idea of limit is it's another way you can use a limit to express the number 1. In this case, we're using the limit to express the number 1 in a different way. Through a never-ending sequence, right? Through a never-ending sequence, we're expressing 1 in a different way. Yeah?
So if you say that n is not, let's say n is 12, can you then say that those are two different numbers?
Absolutely, right? Because you're only going to have 12 nines. And then there's a number between them.
I understand.
Then there's a number between them, like 0.9, whatever. 6, all you have to do is add some more decimal places, you got a number in between.
So this just defines what it, I get it.
Okay, so what do we have? We have our rate function. We got 5 minutes left, right? Okay, so we got our rate function. Our original function, first of all, sorry. Original function is f of x was x squared. And so this is a set of instructions telling us what to do with the input. What set of instructions does this tell us to do with the input? Multiply it by itself or square it. Okay? So our rate function was, our average rate function said, do f of isn't that what we got? For small delta x, we got this here. Because we said the left x virtually becomes just any x value, right? As delta x gets smaller. So if f of x tells us to square whatever the input is, then what is this? What is that? What's the result of that? If the instructions of f of x are to take the input and square it, what will you get for what I put in blue? Tell the person next to you. What will I get for what I put in blue? Just no algebra, just the first step. Just what will that be? So what is this function? It's the square the input function. That's what the instruction, square the input. That's what it does.
So it's x plus change in x squared.
He wants x plus change in x, quantity squared. He wants x plus delta x, quantity squared. That's what it is. The new input here is x plus delta x. And what does this function tell you to do? Square the input. So you're going to square the input. So you're going to take x plus delta x and you're going to square it. What is f of x? X squared. Okay, so x plus delta x squared minus x squared over delta x is this, for our function x squared, is this right here. See that? So we can do a little algebra here. So we can multiply out that top, FOIL it out, and we see that we got an x squared and a minus x squared that can go away. And then, so that's kind of skipping a step there. So x squared minus x squared is 0. And now we're left with this numerator, which we can, I'm going to write it over here. What can we do? We can factor out a delta x. Do you see that? And after factoring out a delta x, now delta x over delta x is 1, and we get this. But what do we say? Delta x is? Okay? We're talking about delta x being very, very small. It's our idea of limit. So they're essentially equal. So they're essentially equal to 2x. So that whole expression there, our rate for this particular function is essentially equal to 2x for sufficiently small values of x.
And is that,
What's that? Yeah.
I know I'm getting ahead of myself,
Yeah.
but that's like that's the derivative basically, right?
This is where we're starting to embark on derivatives. That's right, because the derivative is exact rate from exact accumulation. That's what we're doing. Okay, and what did so when we plotted R of x, what did we get? Can you see that? 1, 2, 2, 4. So we were plotting our R of x. And what function is that? 2x. This is that's what we got when we did in graph and calculator. We made x, took that average rate function, the step function, and made x really, really small, delta x really, really small. We essentially got the graph of 2x, which we just showed algebraically also from we worked this thing out algebraically and saw that that was 2x as well, from what we just did.
Back to the
Yeah.
What do you want us to do with the homework?
Do you want to turn it in Monday, redo it, turn it in Monday?
Yes.
Do that.
Oh, we have 5 minutes.
Totally matches, dude. Yeah, so these are just based on estimates. Also, this is exact. It's a match. I wasn't sure if well, they would have been the same if we would, instead of estimating off the graph, we just would have used the number. Well done. All right, thank you.
So that was just like the opposite of the integral then, right?
We're going the other way.
Yeah, so
Getting rate from accumulation.
that was awesome. That was so cool.
Good. Very good. Yep.
So, I've been messing up on like the homeworks. I looked online like on the syllabus, policy and homework. It doesn't really say like return your homework late or like redo any of them. I was gonna ask you, can I redo some of it just to get the extra points back? Just, 'cause I understand what's going on. I just been messing with the homework.
Yeah, so in the homework is like all you got to do is try and make it look good, and you get full credit.
Yeah,
You know? And
yeah.
So
Like that's
you got to the point is you got to stay on top, stay with it, so that class time is valuable time because you've been thinking about it. That's the whole point of homework. Is you've been thinking about it, so when you get to class, it makes a lot more sense.
okay.
So just
Just work harder.
I would say if you want to do if there's like maybe the last 2 or 3 that you haven't done, do those. But the ones from a long time ago, it's too late for those. But if there's like 2 or 3 that you want to still do, that'd be okay. But then don't from here on out do it every time.
Yeah, and also they're all like online and everything.
It's still the list is all there. Yeah, just go to the homework list and just it's all reverse chronological.
Okay, thank you.
Yep.
We see that limits are like accumulation functions and then just kind of building up.
This one?
Yeah, the tiny little pieces of the changes in X, like our accumulation functions were like when. I don't think I'm explaining myself.
This isn't the right slide. Is this the right slide?
No, it was like further back when we were. We'll have to like ask them to go over it again.
So this is the gray one's the original accumulation function.
Yes.
And the first thing we did was we made a piecewise function of average rates,
Yes.
which are constant rates that have the same change in y, right?
Yes.
And so that's like a pretend function for our actual function. And if we let delta x get small, then that pretend function does better and better to mimic the graph. So if we take the step function for those rates, where's it here? So actually graphing now the average rate. So as the piecewise average rate function does a better job pretending to be the real function, what happens to our step function? It becomes like the real rate function.
Yeah, that's what we're getting at with that limit function that you introduced
Right,
today.
yeah.
So, okay.
Yep, so it's the limit of this as delta x gets very, very small.
Okay.
Yeah.
No, that's how I was trying to explain it to Melody. She's like, I don't know where we're at.
Yeah,
And I felt like I was explaining it, but
Yeah.
not necessarily.
this is, yeah, so, yeah. Okay, who's next?
I'm just gonna ask, okay, that last thing that we were just going over, right? It was 2x plus delta x, did you just, like, cut off the delta x?
Why did we do
Just
that?
like super small?
Because it's
Okay.
small enough so that it's virtually indistinguishable from 2x.
So, like, it just, you just forget about it type thing?
No,
Like,
you
at
don't.
the very end?
You know, well, you let delta x get very, very small, and so then that expression is virtually the same as 2x. So
It kind of merges.
yeah, by saying get rid of it, it's kind of like you're going to get rid of everything before that too. Right? So you want to remember the process, but then the end goal is this exact rate of change function, which when delta x gets very, very small, then we don't have the delta x anymore.
Okay. Yeah.
Cool.
I'm still not sure about the moving the part.
Yeah.
When we were changing the value of A.
Yeah.
So why is it that when you change the value of A, like when you get to a certain point, the intervals like appear to start over, like from where they were?
Yeah, because you moved a at a distance of delta x. So you got a certain value of a. If you increase it by delta x, then you have all the same intervals again, right?
But then how come it still has the same ones from before? Like, because if you're moving the starting value, shouldn't you not see what happened before the starting value?
Okay, so yeah, that's a good question. So just because I decide to start accumulating, say at 3, this still exists,
Oh.
right? So the accumulation up to 3 still exists, even though I said I want to start accumulating at 3.
Oh, that makes sense. Okay.
That's a great question. I wish you
Alright.
would have asked it in class. Yeah, so if I'm starting, so here I'm starting accumulating at 7. It doesn't mean that that accumulation doesn't exist. It's just that for an accumulation function that I'm building, I'm going to start. It's going to be integral from 7 to whatever. You see?
Okay.
So just like over here, if I start accumulating here, I'm accumulating starting at 5.9. Well, x squared still exists for less than 5.9, and it still has a rate. It still has a rate profile.
All right.
Does that help?
Yeah, that makes sense. Thank you.
Yeah, you're welcome.
Oh, I need to ask. It was recording, right?
Yes, it was.
Okay.
And still is now. Let me turn it off. Today is a tough day. Because there's a lot. There's just a lot.